An object is said to be in purely rotational motion when every point in the object moves in a circular path about a fixed axis, which we call the object's axis of rotation. If the wheel shown is in purely rotational motion about an axis through its center, point A and point B on it move in circular paths about the axis of rotation regardless of their distance from it. Not only do they move in circular paths, but they also move with the same angular velocity about the axis. So we can say that all the particles of a body in pure rotation move with the same angular velocity about the axis of rotation. We can therefore call this angular velocity the angular velocity of the entire rotating body. And the same applies to the angular acceleration of the body. We can define the angular acceleration of a rotating body as the angular acceleration with which all the particles of the body rotate about the axis. For a body rotating under constant angular acceleration, we can write the equations of rotational motion as follows. Omega naught is the initial angular velocity of the rotating body. Omega is its angular velocity at time t, alpha is its angular acceleration, and theta is its angular displacement within time t. And these equations are analogous to the equations of motion for translational motion under constant acceleration. To understand the rotation of rigid bodies better, let's solve this problem, which involves a pulley of mass 2 kg and radius 30 cm, having a cord wrapped around it. A constant pulling force of 15 Newton is applied to the cord, making the pulley accelerate uniformly from rest to an angular speed of 30 radians per second in 20 seconds. There's also a frictional torque of 1.5 Newton meters at the axle. We're going to use all of this information to find the moment of inertia of the pulley. First, we'll define the angular acceleration of the pulley using the equation of angular motion, omega equals omega naught plus alpha t. We know that the pulley accelerates to 30 radians per second from rest in 20 seconds. So omega equals 30, omega naught equals 0, and t equals 20. Plugging these values into our equation, we can solve for our angular acceleration and we obtain 1.5 radians per second squared to be the angular acceleration of the pulley. Next, we'll find the net torque on the pulley. We're going to subtract the frictional torque from the torque due to the 15 Newton force because it resists motion in the direction of the 15 Newton force or torque. So our net torque is equal to 15 times 0.3, which is the radius of our pulley, minus 1.5, which is the frictional torque. And we obtain our net torque to be 3 Newton meters. From the angular equivalent of Newton's second law, we know that the net torque equals the moment of inertia of the pulley multiplied by the angular acceleration that this net torque gives the pulley. So the moment of inertia of our pulley is going to be the net torque divided by the angular acceleration of the pulley, which is 3 Newton meter divided by 1.5 radians per second square. And that gives us 2 kg meter square as the moment of inertia of our pulley. Let's consider a slightly different case with the same pulley and cord system. But instead of a constant 15 Newton force pulling on the string, we have a weight of 15 Newtons attached. When left alone, the mass having a weight of 15 Newtons will fall as the pulley rolls. We've already calculated our moment of inertia of the pulley. And since this is the same pulley as before, our moment of inertia is the same. Our aim here is to determine the angular acceleration of the pulley, its angular velocity after 20 seconds, and the distance through which the mass would have fallen in 20 seconds. We're going to start off by analyzing the forces on the block and how they relate to its downward acceleration. The forces acting on it are the tension in the string and its own weight. From Newton's second law, we know that the net force acting on the block is equal to its mass multiplied by its acceleration. So we have 15 minus t, which is the tension in the string, equals ma. And since we know the weight of the block, we can calculate its mass. We know that its weight is equal to its mass times the acceleration due to gravity. So we can obtain its mass from that relation, and we obtain its mass to be 1.53 kilograms. So plugging this value into our equation, we have 15 minus t equals 1.53a. And rearranging it to make t the subject of the formula, we can write t equals 15 minus 1.53a. And we'll call this our equation 1, or our first equation. Next, we're going to analyze the torques on the pulley and how they relate to its angular acceleration. Here, the torques acting on the pulley are the frictional torque and the torque due to the string tension. From the angular equivalent of Newton's second law, we know that the net torque equals the moment of inertia of the pulley multiplied by its angular acceleration. So we can say t times 0.3 meters, which is the radius of the pulley, minus 1.5, which is the frictional torque. And this equals 2 alpha, since its moment of inertia equals 2 kg meter square. And what we have as our second equation is 0.3t minus 1.5 equals 2 alpha. If we substitute t from our first equation into this equation, we arrive at 2 alpha plus 0.459a equals 3, where alpha is the angular acceleration of the pulley and a is the downward acceleration of the block. Now the block and the pulley are going to move with the same linear acceleration since the string connects them both. So we have the relationship between the angular acceleration and the downward acceleration as a equals alpha r, where r is the radius of the pulley. So a equals 0.3 alpha. And if we put this into our equation, we can solve for alpha and we obtain 1.4 radians per second as our angular acceleration of the pulley. For the angular velocity of the pulley after 20 seconds, we use omega equals omega naught plus alpha t. And we can substitute our values into this equation to obtain our angular velocity. We know that omega naught is equal to 0 since the pulley starts from rest, alpha equals 1.4 radians per second square, and t equals 20. So our angular velocity of the pulley is going to be 28 radians per second. To obtain the distance through which the mass has fallen, we can first find the angle through which the pulley has turned through within this time. We're going to use the second equation of angular motion. Theta equals omega naught t plus half alpha t squared. Again, omega naught equals 0, so we're left with theta equals 1 over 2 times 1.4 times 20 squared. And we get theta equals 280 radians. If the pulley turns through this angle, it means that any point on its outer surface would have traveled a distance equal to r theta. This is also the distance through which the mass would have fallen, since it's connected by a string to the outer surface of the pulley. So we can write the distance through which our mass falls as r theta, and this is going to be 0.3 times 280. And this gives us 84 meters.